Welcome, everyone. If you remember last month, we talked about fancy indexing. And we actually had someone try it out, and he did some benchmarking, which maybe publish results. That must be the wrong place. Yeah, right here. So this Leo did some tests, and he's the one who originally got me going on this feature, which is, recall, lets you do point selections through a combination of slices and coordinate indexes. And he used new code with a benchmark. So here's like number of points he's getting. This is the old code in terms of points per second, and versus the new code in points per second. So we have like all the way through, we have like a 4x speed up. So that's great. I'm glad the feature worked and it actually helped performance compared to what he was doing, which was iterating through multiple coordinates. All right. So with that success behind us, let's move on. I want to talk about another issue that's come up with a few users recently. And it's the problem of HDF files that have lots of small objects. And I have an example of what I'm talking about, which I created myself. If you look at this file, is that big enough for you guys? So we have something called a small object at H5, and it's less than a megabyte in size. But if we do h5ls-r, oops, might need a file name, we see there's a whole bunch of groups and data sets. And if we actually look at just the data sets, or data set, we see that they are all one-dimensional with between 1 and 10 elements. Okay, reasonable enough, I guess. The problem is that, and actually I can count these. So we have 200 of these data sets. And if I do an h5 stat on this file, we see that the total space is about a megabyte, and the file metadata is almost all the file, right? The raw data is only 5,000 bytes. So it's a case which is a little unusual, where the metadata in the file is way more than the data in the file. And it's still okay for the H5 library. And to illustrate that, I wrote a little program called dump dsets that you can find in h5pyd examples dump dsets. And let me just walk through the code real quick. So we come in here and get the file name as an argument. And I've done a little trick that I've done a few times in the past, where if the file name starts with s3:// we're going to use this s3fs to open the file. And the file name starts with HDF5://. That's a sign that it's an HSCS domain, not a POSIX file. And we'll use h5pyd.file to open it. And I'll skip over this for now. And otherwise, we just open it as a regular POSIX file. And next, we call visit items, which iterates through each object in the file. And remember, there are hundreds of them. And we come here for each object. If it's not a data set, we ignore it. Otherwise, we read all the data for that data set into a NumPy array. And I'm just going to try calling array mean, array min, array max. And this could be an exception if, say, it was like a string type, but we'll ignore that. And otherwise, we just print the name, the mean, the min, and the max. So let's try that on our file. Small object, psets small object h5. And there it printed out the min, and max for all these data sets. And it took only 0.075 seconds. Okay, so and also I can try this with S3. I have the same file in S3 somewhere. Let me see if I can recall where it is. Okay, so this will be a little bit slower because the latency talking to S3 is a bit more than talking to a POSIX file, of course. But not too bad. So 0.632 seconds. And if we compare that to the other one, it was 0.07. So about an order of magnitude slower to read from S3. But so far, we've just talked about HDF5 files. So what happens if we try to upload this to HSDS? Well, if I do a time, just see how long this takes, hsload small object h5 to home test user 1, my HSDS folder. You can see it takes some time. And it takes time because just like with reading a file through SUFS, here we're seeing each object locally and then having to make requests to HSDS to say create the object, right? And since we have hundreds of objects, it just takes some time to iterate through all these objects to create the HSDS domain. So we see it took like 29 seconds. Okay, and now that we have it loaded in HSDS, we can run that same program with the HSDS path. So if you recall, it's we use HF5 : prefix to indicate we're talking to HSDS. And home test user 1 small object .h5. What's going on? Okay, that's right. Yeah. This name he sets. Oh, it's like all mangled up. Sorry. Down. Hi, sorry. HFI : home test user 1. Okay, I finally got it right. Okay, so now it's running and it took 4.9 seconds, right? Compared to 0.67 seconds with S3FS. So again, it's quite slow because it's having to iterate through each of these objects. And then if we do it again, it should be faster. That's right. Yep, about less than 5 seconds. Um, so that's the basic problem, right? For domains that have large data sets, HSDS can get a lot of advantages because it's able to multiplex these S3 requests to read multiple chunks at the same time, do selections on those chunks, and mangle all together and return it. When we have a domain that has lots of small data sets, you don't really accrue any advantage from that code. So to deal with this, we added this thing called h5image. And if I do hsload, there's a new option called --h5image. And let me just load it up with that option, and I'll explain how it's working. So small object h5, the home test user one, let's call it small object image.h5. Okay, so first thing notice is that the hsload was quite a bit faster than without this --h5image. And the next thing is that if we look at what we created, home test user one small object image.h5, we'll see that it's a h5 image data set called h5 image that is 947,568 elements, which coincidentally is the same size as the file we started with. So what this hsload is doing is actually not trying to replicate each HDF5 object as an HSDS object. Instead, it's creating one data set, and it's basically just taking all the bytes from the file and copying them to that data set. And the advantage is that we can read those bytes as a file image and then operate on them just like a regular HDF5 file. And to see how this works, let's go back to the stump datasets. Recall this part I skipped over. If h5image is in the HSDS domain, we close the domain, and then we call h5pyd.file with this h5image class. h5image is what's known as a file-like object. So it's a class that has properties that enable h5py to treat it like it was a POSIX file. So basically, you can do seeks and reads and puts, and the internals of h5image will do the equivalent gets on S3 to be what the h5py would expect for reading bytes from the file. Now, and there's a little bit of sophistication in this too, because the HDF5 library will oftentimes read very small sections of a file, say to read an attribute. That would be inefficient, again, because you'd be constantly going to S3 to read a few bytes at a time. So instead, what h5image does is it creates a set of pages. And by default, each page is about 2 megabytes. I made it even larger here to be like 16 megabytes. So it'll read 16 megabytes at a time, which means that for a file that's like in our case, it's less than a megabyte, you would read the entire file. If you had a file that was, say, a gigabyte in size, even then, you'd be doing just a few moderately large S3 gets on that data. And when it gets a page, it keeps it in memory. So if the HDF5 library needs that data in the same page, it doesn't need to go to S3. It can just find it in the page. So it's kind of a compromise that, if you just read all the bytes from the S3 object at once, that could take some time for large files. Here, and if you read just the bytes that the HDF library needed, that would be a lot of requests. So we compromise by reading this page at a time. Okay, so that's that. So let's see how this works. Back to our test script. Down psats.py HDF5:// tests user1 small object image.h5. Okay, so that was blazingly fast compared to the HSDS version. So if you recall, that was like this. Let me go back. Okay, so we had 0.12 seconds versus almost 5 seconds. And just to go back even more, let's pull up the S3 one. Right here. So we had 0.6 versus 5 versus 0.68. All right. And then here's the image one more time. 0.12. So I think this would be really useful for people who have this kind of file structure. Now, the two things, I guess. The downside is that you don't have the ability to make HTTP requests to, say, retrieve a particular data set. You have to go through this mechanism of the H5 image. It also, currently at least, doesn't support updating the file. If there were demand for that, we could look into adding that feature. And the other question you could ask is, why not just use S3FS and read HDF files out directly rather than going through all this rigmarole of having HSDS? Sometimes it may make sense to just use S3 directly, but there are a few advantages depending upon the requirements. One is that there can be some speed up based upon the paging in the H5 image class. The other is kind of concerned with if you have an HDF file on S3 that you do not want to make publicly accessible, either because it's proprietary data or just because you don't want, the whole world being able to read your file. It's a little bit tricky to do that in the context of AWS. Whereas with HSDS, we have the ACL mechanism to control access to the file. And just a little refresher. Oops. Or not. My code space is freaked out, but let me just go here. I have the file. Oh, you guys don't see this file. Anyway, so let me just talk about it. So with hsacl, you can control who has access to a file or which groups have access. And these groups or users can be defined in the HSDS password list, or I could use something like Azure Active Directory to have identities that connect to these ACLs in the HSDS domain to control who has access and who can do which operations to the file. All right, so that's all I have for H5 image. So I'll open the floor to questions if anyone has. Okay. Not hearing any questions. Thanks everyone for your time, and we'll catch you next time.
All right. Thank you, John. Bye, everyone.
Okay. Bye-bye.